All right. So my name is Alan Jacobson. I'm the Chief Data and Analytic Officer at Alteryx, and welcome to everyone, and thank you for joining. Today, we're going to do a session on modeling, on artificial intelligence, machine learning, hopefully making this easy to understand and get the concepts. Um, I look forward to having everyone participate. So if you can in the chat window, as I ask questions, if you can try to answer in the chat, that would be absolutely fantastic. So today, when most people think about modeling, they usually think about things like forecasting, predicting the future. But modeling is really about the past, finding patterns in historic data. So you can use a model to understand that pattern of historical data. And yes, if the future looks like the past, then you could use it to forecast the future. But most of the times when I build a model, it's not actually to forecast the future, it's to understand that historical pattern in the data so we can make a decision, we can do something about it. So I'm going to show a set of data on the screen. This is showing people visiting, let's say, a website, the number of times they visit on the x-axis, and how much money they're spending with us on the y-axis. And I'd love for everyone to type into the chat window what pattern they see in this data. And let's see if I can see your comments in the chat window. I'm actually not seeing a chat window. Let's see if we can see you. Does anybody see a pattern here? And Jenna, I'm not seeing a chat window. So are you seeing people type things in the chat? Can you hear me? Hello. It says click on the comments, but I don't see anything that says comments. All right, I think I need some technical help here. I'm going to keep going while somebody gets to me on the side in the chat window and tells me how I can see your comments, or Jen, if you want to say them out loud, the comments that people are typing, that would be great, because I do not see I don't see any comments. So hopefully you see a pattern that's maybe up and to the right, a diagonal pattern through these data points. And if you drew a line, let's say, through the data, which would be a perfectly reasonable thing to do, you probably could do that in your head in seconds, and you probably could do that when you were, I don't know, 2, 3, 4 years old. You could do that when you were pretty young. You could see the pattern in the data in these points. Humans, it turns out, are really good at this machine learning concept. It's machines that actually aren't very good at it. Teaching silicon, your computer, how to find the pattern in this data is actually a little bit harder. And so the computer takes a guess. It draws a line. And so if you like guessing, you'll really like machine learning. So the computer guesses. It says, hey, I'll draw a line. I'll try to go through the data points. How did that work? Did it look good? What do you guys think? Does that look good? Yeah, it doesn't look very good. So the computer tries again and says, how about this? Is it any better? And the computer keeps iterating and trying until it finds a line that'll go through all of the data points. And so in this case, we just did a linear regression. We just drew a line through the data points, and we use a lot of terminology. We say this is positively correlated because as the number of sites increase, the average expenditure increases. And we say it's linear because we drew a line through it. So we use all these fancy words to describe it, but it's a, really simple concept that most of you probably could do at a very young age. Now, does anybody see maybe a more complex pattern through the data that's not a line? Let's see the comments here. Still can't see any comments. Nothing. Jenna, in the chat, you're going to have to give me more direction because I do not see any comments. But maybe you could draw a curve through these data points. This would be a polynomial of some sort. We draw a polynomial curve to fit the data. And we could use more descriptive words about how, it goes slow and then it increases the pace, and then it maybe reaches an asymptote and levels off. And maybe you can see some outliers in this data. Does anybody see an outlier? Maybe like these data points over here. You could debate whether these are outliers or not, but that certainly looks like an outlier. And again, there are mathematical methods to determine what these outliers are. But when you, through your eyes and processing in your neural network, look at this data, you probably very quickly would say, yeah, I see some outliers here. And so this is the foundation of how machine learning works. These are just two models. I just did a linear model, a line, and I just did a polynomial. But we could have other patterns that we work with here. And so I'm going to look at a different set of data here. This is looking at maybe the size of an account and the discount level that's being provided to the account. So when they're really small accounts, we give it a small discount. The medium-sized accounts, we're giving it a medium size, or actually a large discount, and then it goes back down again. The very large accounts are getting a medium discount. So if we look at this data and I said, could you draw a line through these data points? What would you do? Could you draw one line that goes through all of these data points that looks anything like the pattern in this data? And I think that would be pretty hard. I mean, if I drew a line, maybe I draw something like this. Does that really look like any of the data on the screen? And I would say no, it does. That doesn't really represent the pattern that we see on the screen. So we look for different types of models to be able to represent this data. I'll give you a different way of doing it. Here is a model that probably represents that data pretty well. And if you were to articulate, how do we express this model with math? It's really just a bunch of if-then statements. It says, if the account size is between this size and this size, then the discount level is at this level. And if the account size is between here and here, then the discount level is this. And so we call the model on the right a decision tree. It's a bunch of if, then. These are the decisions. And on the left, this is the example that we started with, a linear regression. It's the equation of a line. So two very different model types. Now, if I asked you which type of model is better, what would you say? Do you think the decision tree is better or the linear regression is better? And please, again, type in the Q&A window your comments. Which do you think is better, decision tree or linear regression? And I would say it depends what your data looks like. If your data looks like this kind of data on the left, then the decision tree is going to be much better than a linear regression. A linear regression is going to really struggle with that. And if the data looks like this data on the left, then a linear regression is going to do quite well, and the decision tree is probably not going to be the right answer. And so at the end of the day, finding the right type of model that represents the pattern in the data is really the key to modeling. Now, there are lots of different types of models. Does anybody have a guess as to how many models exist out in the world? If you do, type into the chat window your guess. Be curious how many models you think exist in the world. I haven't tried to ask ChatGPT how many models it thinks are in the world. I should probably do that. That would be entertaining. I don't think I'd believe the answer. And if we wanted to, we could invent a new model right now. Jenna was just on with me, and Jenna said she wanted to create an all-new model. It's going to be called the Jenna model. It's in the shape of a J, so it's a nice big J. When do you think the Jenna model would be great? Any idea when you would want to use the Jenna model? I would say if your data looks like the letter J, then you should probably use the Jenna model. That's going to be a great model for you. And if your model doesn't look like a J, then it's probably not going to be a very good model for you. So every day, researchers sometimes come up with new models that mathematically represent some pattern of historical data. And that's really what modeling is all about. So now, and I think I just learned how to see your comments. And so I'm going to bring that up, although I don't know if they're going to be in English or Arabic. I will warn you, I can respond to your comments much better if they're in English, but if you want to write them in Arabic, hopefully somebody will translate them for me. But I'm now seeing comments, so thank you for that. Those are in Twitter, it looks like, or X now. So I do see those now. So So now we're going to try to do some modeling in your head. So in the United States, we have a practice that I don't think occurs there, but I think you'll be able to imagine this. When you graduate from a university, it's very common that people at the university might call you and ask if you would like to make a donation to the university you went to. And so I want you to imagine you've each been asked to go back to the university that you graduated from, and they've asked you to make some of these phone calls to fellow graduates. And so here we have a list of names of people who graduated from the university. This list would go on, let's say, for millions of rows. It has when the person graduated, and they joined this data, and I can tell just by looking at this, they joined the graduation data, these first two columns, with the donation database. So they looked at how much people had donated and when they donated, and they joined the two together. So they had a table of everyone who's donated, table of everyone who's graduated, joined together, and they get something like this. Now we can tell from this that where it shows the name Chris 3 times, this is not 3 different people. It's the same person that graduated the same year. It's just that they donated multiple times. They live at the same address, right? So this is one person with 3 donations. Hopefully that makes sense. So if I asked you to basically model this in your head, you have to decide who to call, and you can only call one person, and you're trying to raise as much money as you can. I'm curious if you can write in the comments who you would call. Would you call Bruce? Would you call Chris? Or would you call Alan? And tell me why. Why would that be a good guess? And they're all good guesses, but let's try to take some guesses as to who the most likely person would be that's going to donate and give us some money. Any guesses in the chat window? Maybe I have to hit refresh. Let me hit refresh, see if I get some new guesses. Any guesses? I'll give you guys a second to see what you think. Who is the most likely person that's going to donate money if I call them today? Anybody? Jenna, what's your guess? Who would you call? Abo, I'd love to get your guess. Chris. Okay, so someone guessed Chris. That is a great guess, Abo. First guess was Chris, and then I think you guessed the second person you might call would be Bruce. So if you tell me why, like, did you pick Chris? Maybe you picked Chris because he donated 3 times. You saw that he donated 50 in 2017, and it looked like he donated again in 2018, and maybe somebody forgot to put the amount in, and then in 2019, Chris donated again. So you saw that Chris donated 3 times, and you said, hey, that's really frequent. And so you picked Chris. Is that why you picked Chris, Abo? That's a great reason. And again, you can put in the comments if that was the reason. And then I saw somebody also said Bruce, and Bruce is also a good guess. He gave the most money, right? So the biggest magnitude of money. That would be a good reason to pick Bruce. Someone even picked me. They said probably Alan. He's never donated before. Why don't we call Alan? Maybe we've never called him before. All good guesses. These are all good guesses. And so, Abo says the reason he picked Chris was that frequency. And if you think about what you did, Abo, it's actually amazing what you did. In your head, you looked at this data and you basically added a column that's not here. You added a column that said frequency, and you said Alan 0, Chris 3, Bruce 1. And you're going to pick the person with the biggest number, 3. And so you basically added a column in your head. You kind of did some math in your head, and then you used that column to decide to call Chris. And what you just did actually has a name. I don't know if you know what that's called, but the name of adding that column and saying Alan 0, Chris 3, Bruce 1 for frequency, that's called feature engineering. You're restructuring the data based on the way you would predict who is going to call. Now, it turns out recency, frequency, and magnitude, you guys guessed magnitude with Bruce, frequency with Chris, and maybe recency with me that I haven't recently donated. Recency, frequency, and magnitude. It has an acronym, RFM. PhD research papers talk about RFM being one of the best predictors of future human behavior. So, Abo, you probably read those PhD papers last night, knowing you were coming to this talk about AI and ML. No, you probably didn't read the PhD papers. Turns out most people are really good at modeling. They might not know all of the vocabulary. They may not know that that was called feature engineering, but you do this intuitively because as humans, we have great neural networks in our heads. Again, the hard part is teaching a computer to do some of this work for us, but we do this very naturally. And so now we're going to look at some other things we could have done. We could have looked at the addresses and brought in data about what's the level of income typically in these addresses. Are these very expensive, high earning areas, or are these very low earning areas? Do people live in expensive houses or lower priced houses at these addresses? That might give you an indicator of whether they're going to donate significant money or not. So we can bring in some other data as well. But one of the things that we want to do before we build a model is we want to deal with any missing values and see if we can plug in for the missing values. So if I said, what do you think belongs in the red circle? We can see that Chris has donated. Well, it looks like Chris donated 3 times in 2017, in 2018, and 2019, because someone put this date in that was a donation date. And it looks like they just forgot to put the amount in. So if you were to guess, what amount do you think goes in the red circle? What would be your best guess? They donated 50, then they donated some amount, and then they donated 100, evenly spaced 1 year apart. Any guesses as to what you think goes in the red circle here? I'll give a minute for folks to, again, type into the chat. Monitoring here on X to see what we see. Yep. So Abot says this is called data pre-processing for null and duplication. But again, what is your guess as to what this value would be? You would base it on the median of all the numbers, including 2000, or just the median of 50 and 100. I would guess the missing number is probably 75, 50, then 75, then 100. That seems logical. It's just a guess. And what we're doing here actually, again, has a very technical name. The name of what we just did is called imputing a missing value. Fancy word for guessing the missing number. We could have done the same thing for Alan. Again, the blank here, since there's no date, we would assume no money has been donated. And of course, there's no date we can put in because nothing's been donated. So once we've done this, we've filled in the missing values. Now we can restructure the data into the columns that we think are going to be predictive. So we might manipulate the columns to look at the average size of the donation, the frequency of the donations, how long since the last donations. Now we have a column with frequency and recency and magnitude. And so we're actually redesigning the columns to look like the things that we think are predictive of who's going to donate. And so these are just transformations of the data up at the top. You can see we also collapsed where we had 3 line items for Chris. We don't need that. We're just going to have 1 line item for each person with the key characteristics that we think are going to be predictive of the thing that we're trying to predict. So now we're going to take this data and we might do some anonymization of the data. We might suggest that we should protect the privacy of these individuals. And at this step of the process, we no longer need to know who the names of the people are. Now, in this case, we're going to key these IDs. It's not totally scrambled. We didn't delete the column. We keyed it with numbers. And the reason we keyed it is eventually we're going to have to go back to looking at the names. When we go back to the names, it's because someone's got to actually call the people, and the person who calls the person needs to know who they're calling. So we're going to put the name back. But when we put the name back, we might hide some of this other data that the person who's making the phone call doesn't need to know. They don't need to know what we suspect the income is at that address. Not important when they make the phone call. So we'll probably anonymize the data at this step. And then we may rekey the data and drop some columns in the last step to protect the person's privacy. So let's say we've done this. We've now built a model and we're predicting who's going to donate and who's not going to donate. And if I told you on average 2 out of every 100 alumni donate, and we built a model and it's trying to predict who's going to donate and who's not going to donate. If I told you the model is 95% accurate, it can with 95% accuracy tell you who's going to donate, who's not going to donate. Would this be useful for you in order to, use it to decide who to make phone calls to? What do you guys think? Is 95% accuracy good? And I used to, when I was in school, when I got a 95% grade, that was pretty good. But what do you think? Is a 95% accuracy a good enough score to use this? So what I'm going to show you is a way of looking at model accuracy and output to decide if it's good for the purpose of what you're trying to do. And one of the tools that we'll sometimes use to do that is something called, and I hate this name, a confusion matrix. Sounds really confusing already. I wish we didn't name it that, but we've named it the confusion matrix. And so I'm going to show you an example of a model that in this case is actually 98% accurate. So it's even more accurate than 95%. The way you read the confusion matrix is down the vertical, it's showing you what you predicted. So in this case, we predicted 98 plus 2, 100 people. We predicted were not going to donate, and we predicted no one was going to donate. So we said, no one's going to donate, right? So we got the 100 people over here not donating, and over here, 0 people who actually donated. Across the horizontal, we're showing you what actually happened. So of the 100 people I predicted were not going to donate, 98 of them, it got correct because 98 people didn't donate. 2 out of every 100 did, donated. So 98, it got right, and 2, it got wrong. But if I were to implement this model to decide who to call, this model would be telling me to call no one, right? So it's telling me don't call anybody, which I guess would save me a lot of time. I could go home. It saves me a lot of time. But how much money would I raise? This would be none, right? It's telling me don't call anybody because nobody's going to donate, and I'd miss the 2 people who would have donated. So this is actually a 98% accurate model. And it's completely not useful at all, right? This would not help us at all. So let's look at a different model. Let's pretend we built a model. This one has 95% accuracy. It predicted 97 people were not going to donate. It got 2 of them wrong. It said, don't call these 2, but they actually were people I should have called. So it got 2 wrong. And it got 3 wrong that it said, don't call, and they didn't donate. And so, or actually, no, it said it's predicted we should call them and they didn't donate. So here we're calling 3 people, but we're raising no money at all. So again, not a very useful model. Okay. So now we got a 95% accurate model. And again, it's completely useless. So let's try this model. Let's pretend we had a model. In this case, it's 95% accurate. It tells us not to call these 93 people. And indeed, those 93 people don't donate. It narrows the list down to 7. It says, call these 7 people, and 2 of them are going to donate. And you didn't miss anybody. Everyone who's going to donate, you called. What do you think of this model? This seems pretty good, right? So now we're a 95% accurate model, and it's a pretty incredible model. Like, we only have to call 7 of the people, and we can raise 100% of the money. So it's saving us a huge, huge amount of time. So when we look at models, again, just looking at accuracy by itself probably doesn't give us the whole picture. We use tools like the confusion matrix to understand, is the model fit for the purpose of what we're trying to do? Okay, hopefully that made sense to everybody. There are lots of ways we can use models. We can use models in tax and audit and customer support for fraud detection and quality operations. Legal departments use models. Engineering teams, sales teams, marketing teams. The number of use cases for models is really incredible. You see models being used every day. This is an example. With Alteryx, we built a model to look at a hurricane path and predict down to the minute when the power was going to go out at these various locations. These are manufacturing locations for a company that makes bread. And we're able to predict with very good accuracy, within 90% accuracy, when the power will go out and when it will come back on as the storm passes through. So this is a pretty advanced analytic. This is using modeling with geospatial data and time series data. So it's pretty complex. But we have lots of other places that we use these models as well. So I want to show you an example now where we're going to use a model, not as much to predict the future, but again, to understand the pattern of data. And I'm going to bring up an example here. So let me bring up a different window. Hopefully it didn't log me out. And here I'm using alteryx to analyze some HR data, some human resource data. And I'm looking at attrition. I'm looking at what percentage of the people left. So true means true attrition. They left my company. And what percentage of the people stayed? So 84% of the people have stayed, 16% of the people have left. And I want to understand why. Like, why are people leaving? Because I might want to do something to encourage more people to stay. And so I've brought in many other columns of data. I brought in data from a survey on their job satisfaction and their work-life balance. I know their ages. I know how much they travel, if they travel a lot or if they travel a little. I know what departments they work in, how far from home they commute, their education levels, their gender, their job level, their job role. So I brought in a lot of data that might be the guesses as to why they leave. How much money do we pay them? How much of a raise did we give them? How much training have they been doing? How long have they worked at the company? So I put in lots of columns. How many hours on average do they work every day? And now I'm going to say, let's pick the attrition column. So we're going to say for attrition, build, and it automatically says attrition is a yes or a no. So that's a classification problem, not a regression picks a number. Here we're picking a value, and it automatically says, hey, if you pick the attrition column, that's a classification challenge. And now when I hit next, it's going to start building models. It's going to build many, many different types of models and give me basically a scoreboard of which model did the best and which one did the worst, which one could fit the data the best. So now I'm automatically building a model. And here I'm showing a metric for accuracy. I could show lots of other metrics, but we're just going to look at accuracy for a second. And I can see that the baseline model, this is, remember I told you 84% of the people stayed and 16% left. So if we just guessed that everyone was going to stay, we would have an 84% accurate model. We call that the baseline. That's just a naive model, a very simple model. You can see all these other models started to fit the data better and better and better, with the best models being 94% accurate. And actually, the top model here is a model that uses many of the other models combined in a blended model. That's called a stacked ensemble model. So we built many, many models. We did that very fast. But now I'm going to take a look at one of these models to see if I can get insight based on looking at the pattern in that data. And so here I can quickly see these are the drivers of attrition. We can see the number one driver of attrition by far is the number of hours somebody is working. And I might want to dig into that more. So I'm going to go into the advanced insights. So there's the confusion matrix, but I'm going to look at the partial dependency plot. This is going to explain to me what's happening here with the number of hours people are working. So here I can see on the x-axis, the number of hours folks are working. And when they work more than 7 hours a day, on average, 7 days a week, so 49, call it 50 hours a week. When people work 50 hours a week or less, the odds of attrition are about 10%. But when they start working more than 50 hours a week and it starts to get to 60 and 70 hours a week, the attrition rises up to almost 25%. So now we have a decision to make. Do we want to reduce the number of hours each employee works so that attrition goes down? Maybe we hire a couple of extra people, then everybody can work fewer hours. Maybe we take something off of their assigned list of things they need to do. What's the cost of the attrition versus what's the cost of a few employees? And so we can now make a business decision of what we would like to do. And so we have a number of ways of understanding, modeling, and looking at the patterns in the data. So again, this is a way that you can very quickly, you saw how fast that was, bring in data, tell it what you're trying to predict, and then understand the pattern. Now, we didn't build this model in this particular case to be able to predict, hey, Abo, thank you for joining our company. I have a model that's going to predict whether you're going to quit or not. And you don't need to tell me if you want to quit. I'll let you know when it's time to quit. Like, that's not how we're going to use this model. That's not the point of what we're doing here. The purpose of what we're doing here is simply to understand the pattern in the data, understand the drivers that are driving attrition, and then we can make business decisions if we're going to do something about those things. Again, if you have any questions, feel free to put them in the chat. And so now I will pop the PowerPoint back up. So hopefully you can see that, again, while the model is based on historical data, in this example, I wasn't using it really to predict the future. I was using it to understand the past. And so, hopefully you're seeing how easy it can be to use modeling. In the example I just showed, I brought in data, I hit next, 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 and basically all of the work of the modeling was done for me. And so it's very easy to teach people a bit about modeling and give them modern tools. In this case, I was using Alteryx, a very easy to use tool, to allow them to harness the power in that data to get better insights. If any of you are interested in learning more about Alteryx, feel free to reach out to the email address below or in the chat. If you want to type in your email address, we're happy to follow up with you that way as well. But if you want to learn more about Alteryx, more about data and analytics and how to make data dance, don't hesitate to reach out. I hope you had fun today learning a little bit more about structured data analysis and how to do some modeling. And I wish you guys all of the best on your analytic journey. Thank you very much. And I hope everyone has a phenomenal day. Oh, and I did leave my email also in the I think if you click on my icon in the stream, it'll have my email address there as well. You're more than welcome to reach out to me directly or connect on LinkedIn. I'm happy to connect with anybody who would like. Again, my name is Alan Jacobson at Alteryx. Thank you very much.